In this video, I'm going to solve the problem on the board, still on dielectrics. Okay, question says two parallel plates of area 1 meter squared or 1.00 meter squared are given equal and opposite charges of Q equals 30 microcoulomb each. Okay, now a sheet of dielectric of permittivity having a value of 1.5 times 10 to the power of minus 11 coulomb square Newton per Newton per meter squared occupies the space between the plates. Calculate the resultant electric field intensity in the dielectric, and as well as the induced charge per unit area on the face of the dielectric. Okay, now this is quite an important problem. Okay, it will help you understand how to use the formulas that we talked about in our other video on dielectric. So there are some formulas I'm going to be putting here. I'm not going to derive them. Okay, there are formulas that were derived and explained in our other video on dielectric. So still on this playlist, you can check for those ones if you've not watched them, so you can understand how dielectrics work. Okay, now to solve this problem, the first thing they ask us to find is the resultant electric field. Now remember that after the dielectric has been introduced into the capacitor, what happens to the resultant electric field is that it is decreased or it is reduced in its value. Okay, and we said it is reduced in its value, and the new or induced electric field, we say that the induced electric field, okay, is equal to the initial electric field in brackets 1 over the relative 1 minus 1 over the relative permittivity. That's what we said, right? Now the question wants us to find the resultant electric field intensity in the dielectric. Now remember we also said that the resultant electric field intensity in the dielectric is equal to the initial electric field minus the induced electric field, right? So if we choose to substitute what we're having here into this equation, we're going to have E is equal to E naught minus, now induced electric field is E naught in brackets 1 minus 1 over relative permittivity. Okay, so we can choose to substitute in, and we're going to get this will be equal to E naught is constant. We can bring it as, so we're going to have E naught in brackets 1 minus 1. This becomes what now? A plus, right? So we're having 1 here, minus times 1 is minus 1, minus times minus gives you plus. So this one cancels out. So it simply means that the net electric field which we are looking for is equal to the initial electric field divided by the relative permittivity. This is what it simply means. But then we have to first solve for the initial electric field intensity, solve for ER, and then we'll substitute. Okay, so I'm going to take note of this equation, then solve for E naught first. Now we do know from Gaussian's law, we've done Gauss law before, you can as well watch those videos to understand it. Okay, that's from Gaussian's law that the relative the electric field intensity will be equal to the charge divided by the area times permittivity of free space, right? Okay, if that is true, we can as well, we also know that relative permittivity is equal to permittivity of the medium divided by the permittivity of free space. Now if you choose to substitute these two formulas, let's call this 1 and let's call this 2. Now if we substitute both into this equation, okay, by substituting, we're going to get the electric field is going to equal E naught is Q divided by A epsilon naught, okay, A epsilon naught, okay, times, so we're going to switch this one upside down, so we're going to have E naught divided by EM. E naught cancels E naught, okay, so it means the net electric field is going to equal Q divided by A times the relative or rather times the permittivity of the medium. Okay, now we're given the permittivity of the medium in a question which we are going to make use of. It simply means that E is then going to equal, what was the charge given? We had 30 microcoulomb, that is 30 micro is 10 to the power of minus 6, okay, divided by A. The area was 1, okay, it's already in meters, so no need to convert, and then the relative permittivity is 1.5 times 10 to the power of 11, 1.5 times 10 to the power of minus 11. So what are we going to have as E? Okay, we're going to do that on our calculator. The value of E then becomes 30 times 10 to the power of minus 6 divided by 1.5 times 10 to the power of minus 11. Okay, we're going to get a value of 1, 2, 3, 4, 5, 6, we're going to get a value of 2.0 times 10 to the power of 6 Newton meters, okay? Newton per meters rather, okay? Newton per meters. Now, here is the value for the electric field intensity. So that is how a problem like this is being solved. Or you could as well take note that since we know that electric field intensity is given as this formula, okay, from Gauss law, we can replace permittivity of free space with E, or rather epsilon m times relative permittivity. Okay, we could as well do it like that. Okay, I think it will make more sense. And in our other previous video, we also explained how E is equal to E naught divided by E arrow. I said when the dielectric is put into the capacitor, what happens is that the value of E tends to decrease. Okay, it tends to decrease by this value. Okay, so these are another things that you should take note of. Okay, then we just have to substitute for E arrow, of which we know E arrow is this one divided by permittivity of free space. Okay, that is what we're going to get. So that is the value for E. Now, in the next question, they now ask us to find the induced charge per unit area. What is going to be the induced charge per unit area? The induced charge per unit area of the surface. When you talk about induced charge per unit area, it simply means the charge density. Okay, now what will be the charge density? And remember, they are not just asking us to find the charge density, but rather the induced one. Okay, now we also knew that similar to this formula, the induced charge density is being given as initial charge density in brackets 1 minus 1 over relative permittivity. Now we also do not know relative permittivity, of which we can substitute for relative permittivity using this formula. But then, how do we know the initial charge density? Initial charge density is simply the charge, initial charge given in the capacitor divided by the area. So we can then come here and say the induced charge density is going to equal the initial charge given divided by the area in brackets 1 minus 1 over, now relative permittivity is Em over E naught. So if I put Em over E naught here, E naught is going to go up, okay, the E naught is going to go up and the Em comes down. So I'm going to have E naught divided by Em, okay, or epsilon rather, okay, you should know what this means. Now, the induced charge density is then going to equal, Q was given as 30 times 10 to the power of minus 6, okay, because it was given in micro. And area is 1, in bracket, we have 1 minus, permittivity of this space is a constant, which is having a value of 8.85 times 10 to the power of minus 12 divided by, permittivity of the medium was given as 1.5 times 10 to the power of minus 11. So you have 1.5 times 10 to the power of minus 11 as our value. Okay, so I'm going to do that with our calculator and see 30 times 10 to the power of minus 6 times 1 minus 8.85 times 10 to the power of minus 12, okay, over 1.5 times 10 to the power of minus 11. Now, by doing that, we're going to get a value of the induced charge, okay, is then going to equal 1.23 times 10 to the power of minus 5. Induced charge is charge divided by area, so that is coulomb per meter squared. Okay, so that is our value, and that is how a problem like this is being solved. So as promised in our last video, we said we we're going to solve a problem on dielectric, okay, using the formulas, of which I just made use of some of the formulas as well. All you have to do is solve one problems and then you get to it. Now if you have a question, do write to put it in the comment section, and if the video was helpful, don't forget to like, share, and with your friends, and then click on the notification bell so that when more videos are uploaded, you get notified. And before you do that, remember you have to subscribe, okay, so that you can click on the notification bell. Okay, so if you did not get it completely, you might want to rewind the video and go over it again, or watch our previous video on dielectric to help you understand how these formulas are being worked with. Okay, so see you in the next video. Bye.